So, in your notes from Monday, take a look at a system that we might have solved, any system. Maybe the last one, the 3x3 system. Not the one with the funky solution, the one that actually had a solution. Is anybody? Kyle, are you finding one? 3x, maybe, sure. 3x minus 2y.
Plus z equals 4.
Yeah.
Negative 2x, no y.
Right.
Negative 3z.
Negative 3z equals 1. And then
6x plus 4y minus z equals 7.
Plus 4y minus z equals 7. And then we got the solution, right? What was the solution? What? No, yeah, the one with all over 17. Hey, you're looking at the very last one, the one with the funky solution. So yeah, that was, x was like 23, 17, 21, 17. 23, 17. There was a 10, 17 somewhere. And then negative 21, 17. Okay. Is that right? Why was it negative? Somebody tell me what was the answer there. So the negative 23 then? We did have two negatives, right? Okay. Let me just double check. Yeah, negative 10 17s, negative 21, and positive 23. Okay. So negative here. Anyway, it's not that important what I'm trying to do. So basically what this says is that x equals 23 17ths, y equals negative 10, negative 10. I know, just a man and a number. Yeah. That's a system of equations. That's the easiest system of equations. Has three equations, three unknowns. What are the solutions to this system? Can you tell me the solution to this system of equations? What is x? And what is y? And what is z? All right, so when the system of equation appears in this form, it's very easy to solve, right? Now the solution, the system that I just wrote and the original system, they have the same solutions. Do you agree with that? So we call these two systems equivalent, just like equivalent equations. Equations that have identical solutions are called equivalent. Same thing with systems. If you have two systems that have identical solutions, those systems are called equivalent. Now, given choice, which system would you rather solve? The first one or the last one? Last one. That's a very friendly system. If I actually write it in a more precise form, it's actually like that, right? If I actually put spots, here's y equals negative 10 17ths, and then there's z equals negative 21 17ths, right? That's kind of keeping your variables lined up in a pretty kind of way. So we like the systems in this form. Now, it seems like I'm wasting a lot of writing by, putting x's and stuff, but you get the idea, right? If my system looks like that, it's done. There's nothing to solve, right? So we're going to try to do that. We're going to try to find a way to convert our systems into that form through some, what? Well, no, I'm talking about, these two are the same, really. It's just there's no difference between those. I'm just saying between the first one and whatever I just wrote. Okay, how to go from this to that in a kind of a smoother motion. Because the way we were solving before, we were taking a 3x3 system, reducing it to a 2x2 system, solving a 2x2 system, then going back and finding the missing variable. Here I'm actually going to solve the whole system at once, just rearranging terms and making it what we call a diagonal type of form. Okay, so if we're just going to agree that all x's, we're going to write our variables in a order x, y, and z, then even writing those variables is redundant. All I really need are the coefficients. And that's what a matrix is. If I take a look at these equations and I'll just write their coefficients, 3, -2, 1, -2, 0, -3, and then 6, 4, and -1, that's the matrix of coefficients from the equation, right? So that's what the matrix is, just taking the coefficients. When I look at the matrix here on the bottom, then the coefficients are just 1, 0, 0, 0, 1, 0, 0, 0, 1. Right? If I just list the coefficients. Y, z have no coefficient in the first equation, right? 0, 0. X, no z, so has coefficient 0, and so forth. So we like this form. It's called an identity matrix, when it just has ones in a diagonal and zeros everywhere. An identity matrix. Matrix, like a movie. So let me just play with some solving systems by using matrices, okay? Because again, all I need are the coefficients. So here's an example. And we're going to start it kind of slow. So here's a system, 2x minus y plus 4z equals -3. 1x minus 2y minus 10z equals -6, and then 3x no y plus 4z equals 7. Okay? So the way I'm going to convert this system into the matrix, I'm just going to copy the coefficients. Okay? So in the first one, we're going to write 2, -1, 4, 1, -2, -10, and then 3, 0, 4. Is everybody okay? Okay, just wrote the coefficients. Now, if I want to keep it as a system, the way we're writing the right-hand side of the equation, we're putting a vertical bar like that. And we're going to write the equal part, -3, -6, 7. So see what I did? I just copied the coefficients, and the vertical bar, that's all the equal signs. And this is called augmented matrix. What it has, the coefficients in front of the variables together with whatever the equal sign brings. I'm pretty sure there'll be one of the questions on your homework slash. But yeah, if I ask you some of this on the test, you're going to be solving that sucker. It's not going to be that simple. Now, there are 3 legal things that you can do to a matrix right now. Those are the exact things we were doing when solving equations, when we were solving systems. I can rearrange, by the way, these are called rows, and these are called columns. Is that okay? Just making sure we're on the same page. I'm not even labeling it. So I can always rearrange the rows, because then I'm just saying, equation 2 now is equation 1. So the order in which I look at the equations doesn't matter. I cannot rearrange columns now because columns are attached to the x, y, z. So flipping columns, that means I'm just interchanging the coefficients of x and y, and that's just silly. Okay? But interchanging rows is okay. Right? That's one legal move. Second legal move, I can always multiply any row by a non-zero number, and that's we've been doing that before. Taking an equation, multiplying both sides by a number, right? That was the second legal move. And the third legal move, I can always add any two rows together. I can take first row multiplied by 7 and add that to the second row. And we were doing that before with equations. So these are my three legal moves. Now, what I want us to do first, and this is a little easier to do than actually obtain the identity matrix, we're going to do the next best thing. The identity matrix, that's just clear. You just see the answers right away. The next best thing is to do what? Oh, you just no, but you just said the word very close to what I was about to write. I was like, oh, he knows what I'm talking about. But not a sharpener. I just heard something else. The sh sound threw me off. There is the so-called the echelon form of a reduced echelon form. So for some reason, the sharpener reminded me of that word. What that means, you have, just stop it. You have ones in the diagonal, so the diagonal of a matrix is just 1, 1, 1, 1, 1. And then everything, let's say, below the diagonal, just a bunch of zeros. Now above, numbers. So I just want to have ones in the diagonal, everything 0 below, and then a bunch of numbers above. Because then, yeah. Because basically you will get the variable z for free. Then the last row, what's going on over there? Do I need to like play grade school and like move you all in that corner? Well, if you listened, you would have known. Well, you just described what I drew. But you see, this way, I know exactly what z equals to, because the last row just had 0, 0, 0, 0, 1, and then a number. So I know z equals something, so I can go back and resubstitute and find all the variables. Anyways, you'll see how that's going to work. So this is what I want to do. I want to convert this matrix so it starts the top, the leading term we call it is going to be 1, and then the entire diagonal is going to be 1, 1, 1. I'm going to use the magic pen. Don't write anything down. I want this to happen. 1, 1, 1, 0. Oops. Oh, shut up. 0, 0, and a 0 here. These are all zeros. But then 1, 1, 1. All those numbers will change. Okay? So the best way to do that, I see that I have 3 rows. One of them starts with a 1. So I want to take this row and move it on top, because I can do that. I can interchange the rows, so then I have the top row starts with 1 right away. So I'm going to do that. So I'm going to interchange row 1 and row 2. So then I'm going to rewrite this. I'm going to be a lot of writing, as some of you might have pointed out. 1, -2, -10, -6, and then 2, -1, 4, -3, and then 3, 0, 4, 7. Okay? So the way I'm going to do that, I will use this 1 to kill that 2. The way I can do that, I can multiply row 1 by -2 and add it to row 2. Just like we were doing with systems of equations without matrices. We were multiplying equations by a number and adding it to another equation. So we're eliminating, really. That's all we're doing. Is that okay? So I'm going to go -2 times row 1 plus row 2. So what that will give me, again, row 1 will stay the same. And we're going to do some mental mathematics. You ready for that, Willie? Okay. So 1 times negative 2 plus 2 will give me 0. Right? That's what I'm doing. And then negative 2 times negative 2 is what? 4 plus negative 1? 3. So that becomes 3 now. Negative 10 times negative 2 is what? 20 plus 4? 24. And then negative 6 times negative 2? 12. 9. Is that okay? So you just took every number from a top row, multiplied it by negative 2, and added to the second row. So the goal is to get 0 up here. That's what I want. Okay? And I can do the same thing with the third row. I'll just have to multiply first row by negative 3 and add it to the third row to kill that first 3. So I'll do that. I'll do this operation at the same time. Negative 3 times row 1 plus row 3. So now see what happens. Again, you'll get 0 here. But then it's negative 2 times negative 3 is what? 6 plus 0, 6. Negative 10 times negative 3 is 30 plus 4, 34. And then negative 6 times negative 3 is 18. And then there is 7, so 25. This new system is equivalent to the original system. They both have the same solutions because we did not do any illegal moves. We stayed with our 3 available operations. Interchange row and do constant multiple, add with something else. Are my numbers correct? Okay. So you see the first column, I'm very happy about this first column. Then I'm looking at this number. What I want that number to be? 1. How do I turn 3 into 1? Well, then I'll get 0. But again, remember, my moves are multiplying rows by numbers. So can I just do that right away? Can I multiply what? You can subtract rows. Yeah, just take this whole row and just multiply it by 1/3. Just divide everything by 3. That's perfectly legal, right? So I'm going to write this new system again. 1, negative 2, negative 10, 6. Now it's 0, 1, 8, and 3. Right? Dividing everything by 3. And then 0, 6, 34, 25. Now, remember that I'm already happy with my first row. I'm now happy with my second row because I have 0, 1. I have the 1s in the diagonal. I'm not so happy with the third row. I need to get rid of this 6. And the way I'm going to do that, I'm going to use this 1 to kill the 6. And the nice thing about having 0 in here, since I already have 0 as in the first place, it will not affect the 0 in the bottom. And the way we do this, we're going to take the row 2 times negative 6, add it to row 3. These 2 zeros will not change. They'll still be zeros because, you're multiplying zeros by whatever. It's still 0. You add zeros, it's still 0. But it will kill that 6. Does that make sense? So the next operation here would be negative 6 times row 2 plus row 3. So let's see. We have 1, negative 2, negative 10. 6, 0, 1, 8, 3, and then 0, 0. Now I have to be a little more careful. Negative 6 times 8. Negative 48 plus 34. Negative 48 plus 34. Negative 14. And then negative 6. Ugh. Oh well. What? That's 6? Oh, whoa. Okay, okay. We haven't used it yet. Okay, that's good. All right. Good catch. Because I was already like, oh crap, it's not coming out. Negative 6 times negative 6 is what? No, no, no. I don't need that negative 6. Yeah. Let's go back to this. 3. So, yeah, still not coming out crappy. Why is it coming out crappy? Negative 18 plus 25? Negative 7. Hmm. That's not good. Is that right? Oh, yeah, positive 7. But still kind of. Oh, no, that's correct. Okay, good question. What do you want to do with 14? Well, what do you want that 14 to be? A 1. How do you turn negative 14 into 1? Divide by negative 14. So multiply this whole thing by negative 14. So then we'll get 1, negative 2, negative 10, negative 6, 0, 1, 8, 3, and then 0, 0, 1, and then negative 1 half. Right? If you divide everything by negative 14. That's what we want. Yes. Because now, what does z equal to? Right away. Negative 1 half. The third row tells you z equals negative 1 half. If you know that z equals negative 1 half, you can go to the upper equation. You know that z is 1 half, you can find y. And then you know z and y, you can go one step up and find x. So let me finish this problem. So right away, check this out. This means z equals negative 1 half. You all agree with that? Okay. Now, the second row is really this. It's y plus 8z equals 3. That's the second row. And z equals negative 1 half. I can substitute. So this is y equals 8 times negative, I'm sorry, not equals. It is y plus 8 times negative 1 half equals 3. So this is y minus 4 equals 3. So y equals 7. Right? So then I know z and y, and I can go back to the first row, plug z, y, and find x. So kind of the back substitution still there. So then row 1 is x minus 2y minus 10z equals negative 6. And then you just substitute everything that you know. Minus 2 times 7 minus 10 times negative 1 half equals negative 6. So I have my x, right? X minus 14 plus 5 equals negative 6. So x is what? 3? Is that right? Because this is negative 9, right? And negative 9 added to the other side, that's 3, right? Negative 9, when you're adding it, I don't know yet. Yes, it is 3. 3, 7, negative 1. So the solution is 3, 7, negative 1. Negative 1 half, yes. So, did that make sense? I know. Thank you. Again, just hey, see, this thing now makes sense. Okay. Now it will make bigger sense if I make the top equal 0 as well. Then it's really easy. Then we have our identity matrix. Right? Because we just kind of, really, this is almost half-assing the work. Because now I can go back. Now I can use this one to kill that 8 and to kill that 10. Sure. And then I can use this one to kill that -2. And then I'll get the diagonal matrix, see? And then the things here would be 3, 7, -1/2. No. But yeah, it is. It might feel a bit of an overkill because, like, well, because we're already kind of, it's already easy enough. What? No, believe me, this is.
See how far you can scroll.
Yeah. Well, do you remember problems from Monday? They were even longer when we were. Yeah, the -21/17s. Okay, so now this technique, by the way, of using that leading one to clear out everything below it. See, that's what we did. We got one in the first place. And if we didn't have a matrix that started with one, then find the row that's, easily converted to one. What I mean by that, if I have, let's say, 2, and then the rest of them are even, then I can just divide everything by 2 to make first one 1. See which one is easiest to divide by. So get that one, and then use that one to kill everything. What just happened? To kill everything below that one. And that's what we did here. Right? Then get another one. Use it to kill everything below. And then get the last one. This process is called Gaussian elimination. Don't Jesus. Well, it's kind of Jesus in mathematics, Mr. Gauss. He's the math Jesus, so yes. So the Gaussian after a good man called Gauss. Do you know Gauss? You should know Gauss. What? What? What is he talking about?
After Gauss.
Yeah.
It was supposed to be quotation.
Oh, Jesus Christ. See? He brings the best in us. Yes. Pray to Gauss. If you are ever asked name some mathematicians and you don't drop the Gauss name, you're wasting someone's time. This is easily top 3 dudes in math. Oh, he was okay. He died at a normal, humane age. Yeah. Oh, that's a good question. Yeah, the last one was correct. GAU. Gaussian elimination. No, that's a U. Oh yeah, in the end, that's an N. Gaussian. All right. So yeah, he's big on math. He's very famous. Did a lot of work. And yeah, we should know good old Gauss. So that's called Gaussian elimination when you get that reduced row echelon form of 1, 1, 1. Okay? There is another thing called Gauss, and this is pronounced as Jordan, not Jordan. It's a Gauss-Jordan elimination. And this is where you do it till you get the identity matrix. Okay? So you get your row reduced form, and then you go back and kill the rest of the coefficients, and you just get, yeah, there's just all zeros, so just ones in the diagonal. That's the Gauss-Jordan elimination. So let's do an example of that. And I'm just gonna go crazy on you if you don't mind. No. Gaussian elimination, I mean, the technique is kind of the same. The goal of Gaussian elimination to get this reduced form, zeros here, ones, and then whatever. Yeah. What we're about to do is going to be Gauss-Jordan, where you have the identity matrix. Okay, and I'm just going to do this to you. Negative 2w plus 2x plus 2y minus 2z equals negative 10. And then I have w plus x plus y plus z equals negative 5. And then we have 3w plus x minus y plus 4z equals negative 2. And then I have w plus 3x minus 2y plus 2z equals negative 6. That's 4 equations for a known system. Doing the cutie thing we did on Monday might not work. Because remember what we did on Monday, we went from 3 system to 2 system. That means we have to take 4 by 4, make it into 3 by 3, make that into 2 by 2, solve the 2 by 2, go back into 3 by 3, find the third variable, and go back to the find the fourth. But anyways, it's going to be messy. We're better just think of this as a matrix and just kill everything, get ones in the middle, kill it off. So if I write this as a matrix, it is negative 2, 2, 2, negative 2, negative 10, 1, 1, 1, 1, negative 5, 3, 1, negative 1, 4, negative 2, and then 1, 3, negative 2, 2, negative 6. Right away, you see how much easier it is to think of this as a matrix where you don't need to carry all the variables, right? Those are just the coefficients. I hope I copied them correctly. So again, remember, in order for me to start killing things, so I'm going to start with the first column. In order for me to kill the first column, the very leading term, the first entry, has to be 1. Few ways to do that. I can just divide the top row by negative 2. It will work just fine. I can interchange the first and the second row, or first and the last row. Basically, I just want to see 1 where the negative 2 is, right? So there are many ways to get that done. How do you want to do it? You want to just flip the 2 rows to get 1 in there? Doesn't matter. Oh, you already did that? That's fine. Who said that? Oh, divide it. I thought, okay, let's divide it. Doesn't matter. Divide everything by negative 1. I'm sorry, negative 2. So multiply the top row by negative 1/2, which is fine. Again, we just need to see 1 as the leading term. So it's 1, negative 1, negative 1, 1, 5, and then 1, 1, 1, 1, negative 5, and then 3, 1, negative 1, 4, negative 2, and then 1, 3, negative 2, 2, negative 6. So now I'm going to do what? Row 1, the first row times negative 1, add to the second row. Row 1 times negative 3 added to the third row. Row 1 times negative 1 added to the fourth row. So basically, minus 1, minus 3, minus 1. That's how you want to do that, right? So I'm going to do 3 operations. So it's negative 1 times row 1 plus row 2. So the first row stays unchanged. Then we'll get 0. And then negative 1 times negative 1 is 1, plus 1, 2, and then another 2, and then a 0, and then negative 10. Do you agree with that? And you should be able to do that. I think that's right. Is that right? So I'm multiplying each element of the first row by -1 and adding it to the second row. So this is 1 plus 1 is 2, 1 plus 1 is 2, minus 1 plus 1 is 0, -5 is -10. At the same time, we're going to take -3 times row 1 plus row 3 to kill the leading term in the third row, so that's 0. So -1 times -3 is 3 plus 1, that's a 4. -1 times -3 is 3, -1 gives me a 2. -1 times -3, I'm sorry, +1 times -3 is -3 plus 4 is 1. And then +5 times -3 is -15 with a -2, -17. Is that okay? Somebody computing that parallel with me just to match the numbers, or you're just copying? Somebody just. I'm not sure yet. So I did -3 times 5 is -15, right? And then -15 plus -2 is -17, right? Because I'm multiplying the first row by -3 to kill that. Is that right? Yeah, I could have done that. But I mean, with the way it was originally, I could have done that too. Yeah. But I mean, again, there's so many options. As long as you don't violate those 3 rules, we're going to be okay. Again, we can have, all of us, if we just sit down and do this problem, we can get 9 different solutions will come to the same answer. Because how you get there, it's really, varies. Now, -1, we're going to multiply top row by -1 and add it to the row 4, so we'll get 0, right? Then -1 times -1 is +1 plus 3, that's a 4. -1 times -1 is +1, -2 is -1. -1 times +1 is -1, plus 2 is 1. 5 times -1 is -5, plus -6 is -11. Right? I think that's right. I don't know. Now I want this place to be 1 as well. Now it's the easiest thing to do is just to divide the second row by 2, and then you just get your 1. Everything else will be pretty, right? I mean, I can divide that one by 4 and move it up, but I'll get a whole bunch of fractions. So the easiest one to obtain is this one, right? So it's going to multiply the second row by 1/2. So I'm just going to copy the whole new system. 1, -1, -1, 1, 5, 0, 1, 1, 0, -5, 0, 4, 2, 1, -17, 0, 4, -1, 1, -11. Right? So then I can use this 1 to kill this 4 and that 4. Right? I can actually now use this 1 to kill the 1 right above it. Because you see, just having 0 up front, if I add row 2 to row 1, I'll get 1, 0, 0. Right? And then other things. So we can kind of mix it up a little bit. But just keep that one in mind. I want now, since I'm going for the identity matrix, I want the second column to be all zeros except for that second entry. So anyway, so we'll do just row 1 plus row 2, and that's going to be my new row 1. So it's, if I just add them, I'll get 1, 0, 0, 1, and then 0. Right? I'm just adding row 2 to row 1. Is that okay? So 1 plus 0 is 1, negative 1 plus 1 is 0, negative 1 plus 1 is 0, 1 plus 0 is 1, 5 negative 5 is 0. The second row stays the same for now, 0, 1, 1, 0, negative 5. And then we're going to do negative 4 times row 2 added to row 3, and negative 4 times row 2 added to row 4. So we're going to use this one to kill the 2 4s on the bottom. So why is it jumping? Okay, so it's 0, 0, 0, 0. Now, row 1 times negative, sorry, row 2 times negative 4. So it's 1 times negative 4 is negative 4, plus 2 is negative 2. 0 times negative 4 is 0, plus 1 is 1. Negative 4 times negative 5 is positive 20, negative 17 gives me 3. So that's my new row 3. And row 4, same way, we're going to get 0, 0. And then it's 1 times negative 4 is negative 4, plus negative 1 is negative 5. 0 gives me 1. And then that's 20, negative 11, so that's a 9. Negative 2. All we're doing is just multiplying and adding, multiplying and adding. We're not doing anything fancy. But now things about to get a little naughty. Okay? Why did I say that? Why are things getting naughty? Well, yeah, but again, my goal is to have 1 in this spot now, right? So the way to get 1 here is to just divide everything by negative 2, so that creates fractions. Or to get 1 here, divide everything by negative 5, that creates fractions, right? I don't like fractions either. But that's what we technically have to do. Again, as I said, there is no correct, you must do this step type of deal here. We can get very creative. What I noticed, because I've done this before, see what happens. If I just take row 2, because again, you can do whatever you want, just don't affect this part, because these are already zeros, they're beautiful, don't mess with them. Okay, because they're actually good, because when I start adding those things up, they don't change anything in the first 2 columns. But what I notice, if I take row 2, I'm sorry, this is row 3. If I take row 3 and I subtract row 4 from it, what will happen? It's negative 2 minus negative 5 gives me what? 3. What? Yeah, negative 2 minus negative 5 is 3. What is 1 minus 1? 0. And what is 3 minus 9? Negative 6. 3 and a 6. Now I can divide by 3. Right? What? 3. Because again, we can go ahead and get into fractions. It'll just be ugly. But just as a recommendation, because do you see that what I'm talking about? If you subtract those 2 rows, you'll get numbers that are going to be easier to work with, and you're going to get that 0 that you want over there anyways. So check this out. So I want to do this step. Row 2 minus row 3. So if we do that, we'll get 1, 0, 0, 1, 0. 0, 1, 1, 0, negative 5. And then when I subtract, I'll get 0, 0, 3, 0, negative 6. Yes, I meant row 3 minus row 4. Thank you. Thank you. Yeah, it's hard to keep track of the rows. 0, 0, negative 5, 1, and a 9. Yeah. Well, we don't want that 3, but now if I divide everything by 3, I don't have fractions. Right?
So divide row 3 by 3?
Yeah. So just divide row 3 by 3. So this will give me, again, 1, 0, 0, 1, 0, 0, 1, 1, 0, negative 5, and then 0, 0, 1, 0, negative 2, and then 0, 0, negative 5, 1, and a 9. Is that okay? So then I can use this newly developed 1 in row 3 to kill the 1 above it and negative 5 below it. I already have 0 over there, so I'm happy. See that? So I can use this unit to kill the 1 above and the 1 below. So I'll just subtract, row 2 minus row 3. We can do that, right? I'm just going to write row 2 minus row 3, and then 5 times row 3 plus row 4 to kill the negative 5. See that? So then it's 1, 0, 0, 1, 0. So when I see how easy it is to subtract now when most of the terms are zeros, you'll get 0, 1, 0, 0, and then it is negative 5 minus negative 2, so that's negative 3, right? So I already know what this variable is, right? It's negative 3. What was our second position? It was just x, right? So start with w. So x is negative 3. But anyways, we'll get to the point. Then it is 0, 0, 1, 0, negative 2. Well, I know what this position is now, negative 2. And then when I add, I'll get 0, 0, 0, 1, right? And then 5. So negative 5 times negative 2 is negative 10 plus 9, negative 1. Yeah. And now the only thing I have left is to kill this little guy, right? That's the only one that separates us from the true identity matrix. So we're just going to go row 1 minus row 4, right? And we're done. So row 1 minus row 4, and then the final completely reduced. We'll just get positive 1 in there, right? Because that's 0 minus negative 1. And then 0, 1, 0, 0, negative 3, 0, 0, 1, 0, negative 2, 0, 0, 0, 1, negative 1. So then these are my solutions. The first variable, w, was 1, x is negative 3, y is negative 2, z is negative 1. So it gives me all the answers. Ooh, well, wasn't that fun?
What was that called? The Gaussian elimination?
Gaussian. Gaussian Jordan elimination.
Actually made a lot of sense.
Why so surprised? It is nasty. I'm not. We got the correct answer too. Well, so there is logic to it. When Gauss was a little boy in Germany, or should I say in Prussia, he was. It's a true story. He was in whatever first grade, the class was being, misbehaving in the math class as you do. And the teacher got mad and made kids an assignment to add all integers from 1 to 100. So just you do that, and then you get to go home type of deal. How, if I ask you this, add everything from 1 to 100 without a calculator, but even with a calculator, how long will it take you? No, it won't take a day or two to add. But yeah, if you do it without a calculator. What? So the teacher gave that assignment to the class, and little Gauss was just kind of sitting there, just not doing the work. And the teacher was like, well, little Gauss, what gives? And the guy was like, well, I'm done. He's like, what do you mean? He's like, well, the answer is 5,050. And the teacher's like, well, that's actually true. Well, how did you do that? And the little Gauss was, and he was little Gauss, like 8 years old or whatever. He said, like, well, if I list all those numbers in a row, all the numbers that I need to add, right? And if I add the first and the last, I'll get 101. And if I add the second and the one before last, I'll get 101. I'll get 3 and 98, I'll get 101. And 4 and 97, I'll get 101. And they'll meet in the middle. So how many of those 101s are we going to get? 50. So 101 times 50 is 5,050. So that's how he added the numbers from 1 to 100. Yeah, that was Gauss. I don't know, 8 maybe. Not that he discovered that. That was kind of, that wasn't a new thing. People knew, yeah, you can add, there are fancy ways to add numbers. By the way, this is how you add numbers. If you ask me to add any consecutive integers from 1 to whatever, all you have to do is to really, this is the formula. The sum of all numbers up to n would be n times n plus 1 over 2. So you see that n over 2, 100 is n, so that's your 50. So if you want to add all numbers from 1 to 78, it's going to be 78 times 79 over 2. So that's the sum of all numbers from 1 to 78. I mean integers. Yeah, it's a famous formula. You're just adding consecutive integers. But, when you're 8 years old and you just kind of, well, clearly that's how you add numbers. That's something special. What? Yeah, he got to go home early. Anyway, so let's say I have a matrix. And we usually use capital letters to represent a matrix. Matrix A. And it has elements in that matrix. Let's say the first element, we label it as A sub 1, 1. And the second one, we'll label it as A sub 1, 2, A sub 1, 3, all the way to A sub 1. I just want to be consistent, n. So the first number, when in that little subscript, the first number tells me the row, the second number tells me the column. So when you look at the entry with the subscript 1, 2, that means first row, second column. Okay? So it keeps going like that. This is a second row, first column, a 2, 2, a 2, 3, and so forth, all the way to A to N. And the last one here would be A Mn, if I allow this to be a bunch of entries in there. So this is the M by N matrix. So M would be the number of rows, and N would be the number of columns. Okay? That's how we determine the size of a matrix. Everything we kind of dealt with before was always a square matrix, right? It's a 4 by 4. 4 rows, 4 columns, square matrix, but it doesn't have to be a square matrix. So it's a number of rows by the number of columns, and then each has its address. Okay, so the first number is the row, the second number is the column. Now, you can add matrices of the same size. Okay, it makes sense to be able to take a matrix and add it with another matrix. So, for example, let's say I have matrix A that is -5, 0, 4 and 1/2. So it's just 2 by 2 matrix, and a matrix B, and let's say B is 6, -3, 2 and 3. And I can do wonders with that. I can add them, I can subtract them, I can do basic arithmetic on these matrices. So for example, if I ask you what is A plus B is, well, you're just adding the corresponding components. So you'll take -5 and you add it with a +6, you'll get 1. You'll take 0 and you'll add it with -3, you'll get -3. Right? You'll take 4 and you add it with a 2, you'll get a 6. And you'll take 1/2 and you add it with a 3, you'll get 3/2. No, what? 3.5. Yeah, here we go. That's what you get. Right? So you're just adding the components, very natural, nothing fancy. We can add two matrices, we can subtract. Why am I having problems with this scroll down thing today? So since we're adding the matrices like that, we're just adding the components, the addition, the matrix addition is commutative. So adding A plus B would be the same as adding B plus A. So the order of addition does not matter. So matrix addition commutes, has the commutative property. So actually has most of the properties of real numbers except for the products. So I want to do, well, let's take this example. Matrix A is a 3 by 2 matrix, 1, 3, -1, 5, 6, 0, and matrix B is -1, -2, 1, -2, -3, and a 1. So another 3 by 2 matrix, 3 rows, 2 columns. And let's say I want us to compute a new matrix B minus A. So again, we just have to take corresponding entries and subtract them. So what will be the first element here? So it's B minus A, -1 minus 1, which is -2, right? And then it's -2 minus 3, so it's -5. Okay? It's 1 minus -1, so that's +2. -2 minus 5, -7. -3 minus 6 is -9, and then 1 minus 0 is 1. Is that okay? Very straightforward. So you add, subtract matrices how you would expect you add, subtract matrices. We can also multiply matrices by a constant. We call it a scalar multiple of a matrix. So that's multiplying matrix by a constant. So if I have a matrix, I want to multiply it by 2. That means I'm going to multiply each element in that matrix by 2. Okay? So let's say matrix A is 1, 3, -2, 7, 1, -1. It's a 2 by 3 matrix. And I want to know what is 2A equals to. So I'm just going to double everything. Just everything gets multiplied by 2. So 2, 6, negative 4, 14, 2, negative 2. So that's pretty okay, right? Nothing fancy. Now, there was a day, long time ago, in this class though, when we learned about complex numbers. Remember that? That was back in chapter, don't remember, 2, 3. And I started talking about, kind of lost my mind at the end of the class. I talked about the additive inverses and multiplicative inverses and how we need them to solve equations. And thank God all real numbers have multiplicative inverses except for 0, and then all real numbers definitely have additive inverses, meaning, 5, and if I add negative 5 to 5, I'll get 0, and the 0 is the additive identity, and the 1 is the multiplicative identity. Remember all that? Good. Well, same thing goes for the matrices. Matrices do have additive identity, meaning, can you think of here's an example. I'm glad you're paying attention. Here's a matrix, 1, 1, 2, 3. Okay? What kind of a matrix can I add to the matrix 1, 1, 2, 3? So the answer is a matrix 1, 1, 2, 3. So nothing changes. 0, right? So there should be some kind of a concept of a 0 with matrices, the additive identity, meaning if I add something, things don't change. So there is such thing as a 0 matrix, It just has all zeros. So A plus the 0 matrix is just going to be A. Right? So that's the additive identity or 0 matrix. Okay? So that also means if I take matrix A and I add the opposite of A, the negative A to it, what do you think will happen? 0, right? I'm just subtracting same terms. I'll get the 0 matrix. So this is the additive inverse. Every matrix has an additive inverse. So when you add them, you get a 0 matrix. Okay? So that exists. We also have the multiplicative identity. Okay, so if I take matrix A and I multiply it by another matrix, we still get matrix A. Okay, so the question is there a multiplicative identity? So meaning, if let's call it I, if I take a matrix I and I multiply it with A, I get the same thing back. So I is the identity matrix. And I already used that term. Right? Didn't I drop a term identity matrix? That's the one that just has ones in the diagonal and zeros everywhere. So that would be the identity matrix is that thing. However many ones. And it is always n by n. It's always a square. So if I multiply any matrix, by that identity matrix, I should get my A back. Okay? Now the only question is, well, how in the hell do you multiply matrices? Because that's we haven't talked about that. And that thing is a little weird. Okay? And again, if this made just this much sense, that's all I need. If it made no sense, just a little bit of sense. So matrix multiplication. This one is weird. Now, the way your book defines the matrix multiplication, I just want to make sure I have my subscripts correctly. going to confuse us. Anyways, I'm just giving you an example how we multiply. So let's say I have two matrices. A is 3, 1, -1, and 2, 0, 3. And B is 1, 3, -2, 6, -5, and a 4. So here are the two matrices. The way we define the matrix multiplication, and this is really tricky, we cannot just multiply any two matrices. There got to be some connections there. The first matrix is what? That's, what is the size? 2 by 3. It's 2 by 3. The second matrix is 3 by 2. These two numbers have to match. No, not these two numbers. Let me go back. What has to match? Yeah, these two numbers have to match. Because I can I do that? Yeah, these two have to match. The number of columns in the first matrix has to correspond with the number of rows in the second matrix. And the way we do that, we're gonna the size of the answer is gonna be this. Yeah, we're gonna end up with a 2 by 2 matrix when we multiply it like that. And the way we do that, this first entry is going to be the product of the first row with the first column. And what I mean by that, we're going to multiply first number with the first number, second number with the second number, third number with the third number, and add those products. Okay? So, and this is weird. It's kind of a weird operation, but what will happen here, it is 3 times 1 plus 1 times 3, and then plus -1 times -2. That is just the first entry in the product matrix. I'm just multiplying each numbers like that. Bam, bam, bam. Okay? Does that make sense? Now, for the next entry, we're going to take the first row and multiplying with the second column in the same fashion. We're going to go 3 times 6 plus 1 times -5 plus what? Yeah, so that's the first number, that's the next number. This is a weird process. What? This is so great? Oh, okay. I thought I heard sarcasm, but now I see sincerity. Okay, good. This is fun because there's a gift in the end of all of that.
Well, this is actually making sense. Like, I'm actually seeing it move back instantaneously.
I'm not sure what you mean.
Like how it's connecting all together.
Oh, well, I'm not there yet. I'll give you there'll be a surprise in the end. Okay. Well, good. That's usually what happens every day. Well, then guess what? For the next one, we'll be multiplying the second row with the first column and then the second row with the second column to get the bottom two. So it'll be 2 times 1 plus 0 times 3 plus 3 times -2, and then 2 times 6 plus 0 times -5 plus 3 times 4. Right? So if I compute that, this is 3, 3, and a 2. 3 plus 3 plus 2 is 8. Is that right? Then this is 18 minus 5 minus 4. That looks like a 9. And then this is 2 minus 6. That's -4. And this is 12 plus 12, 24. Is that even correct? 8, 9, negative 4, 24. Yep. Right? Now, just try and tell me what, just flip the order. Go B times A. Well, let's do it together. It's a little messy. I don't know. So I'm kind of working it backwards, right? Let me copy those things over again. What is A? 3, 1, negative 1, 2, 3, right? And the B is, no, 1, 6, 3, negative 5, and negative 2 and a 4. Yeah, it was always 1, wasn't it? Yeah, it is 1. Oh, it's a bracket. It's a brackety thingy. Well, B times A. So now I have to multiply this rows by this little columns. Right? So see what's going to happen now. It is 1 times 3 plus 6 times 2. So that's the first row with the first column. And then I'm going to do first row with the second column. So that's 1 times 1 plus 6 times 0. And then the first row with a third column. So that's 1 times negative 1 plus 6 times 3. Is that right? So if you just compute it right away, so it looks like a 15, 1, and 17. Make sure. Yeah, that looks good. Then we'll do the same thing with the second row times the first column, second column, third column. So we'll get 3 times 3 plus negative 5 times 2, right? I'm multiplying this guy with that guy. And then we'll do this guy with the middle guy, so that will give me 3 times 1 plus negative 5 times 0, and then 3 times negative 1 plus negative 5 times 3. So we'll end up with 9 minus 10, so negative 1, 3, and then negative 4, negative 3 minus 15, negative 18. Is that right? Yeah, that is right. We're actually ending up with the 3 by 3 matrices. So again, the 2s by 2s and the 3 by 3. 2 by 2 have to meet on the inside. 3 by 3 will tell you the size of the matrix. Okay? So the number of the rows has to match with the number of the columns in order for the product to make sense. The outer numbers do not have to match. I mean, I can keep, if I have 3 rows, yeah, with the 3 columns, but how many columns I have here doesn't matter. So the final one is, so with the negative 2, right? So it's negative 2 times 3 plus 4 times 2, and then negative 2 times 1 plus 4 times 0, and then negative 2 times negative 1 plus, is here okay? So what does that give me? Negative 6 plus 8 is 2, negative 2, 2 and 12, 14. 2, negative 2, 14. How's that? Now what you should notice right away, that A times B is very different from B times A, right? So the matrix multiplication does not commute. Addition commuted. A plus B equals B plus A, but from here you see that A times B does not equal to B times A. How's that? Is that okay? All right. So this gives us a kind of a weird way to look at the systems of equations. And which one I want to... Take a look at this system. 2, no. 3, no. Not find the right number, sorry. 1, here we go. X plus 2y minus z actually, never mind. Where's my... I had a good problem here. No, okay, no. Sorry about that. Let's try this again. X plus 2y minus z equals... I didn't have the equal part. How about 2? I'm not saying it's going to come out pretty. 3x plus 5y plus 3z equals 1. And 2x plus 4y plus 3z equals negative 1. Okay? The way, I mean, we already understand how to write this in, in augmented matrix kind of notation. But I can use matrix multiplication now to rewrite this system, because look, what I see now, I have this matrix, 1, 2, negative 1, 3, 5, 3, 2, 4, 3, multiplied with a very peculiar matrix that just has x, y, and z in it. Think about this. If I multiply this 3 by 3 matrix with this 3 by 1 matrix, I get what? X 2 plus 2y minus z, that's that. 3x plus 5y plus 3z, that's that. 2x plus 4y plus 3z, that's that. Right? I mean, so that the left-hand side of my system can be represented as a matrix multiplication here. While the guy on the right, I can think of that as another little matrix, 2, 1, negative 1, my solution matrix. So this is just your regular linear equation format. Some matrix, so the number times the variable equals some other number, right? I don't know what your book calls that number. Could be anything. I'll make sure I have the right notation. Yeah, B, whatever. So B. Okay? Now, if this is just a linear equation, how do you solve that? Forget about the matrices. If the equation is A times X equals B, how do you solve that? Divide by A. What does that mean? Why do you divide by A? Let me ask it the other way. By itself, right? So you're looking for something to kill the A, right? So you're multiplying by 1 over A. So the A's cancel, and you multiply by 1 over A. So you're applying what we call the multiplicative inverse, because they just go away, and you're just left with the variable, right? So the question is, well, can I do this with matrices? Yes. Now keep in mind, matrices do not commute, right? So I have to be very careful how I multiply things. So I'm going to tell you, consider this matrix. And I'm just giving you a bit of a preview. So here's a weird matrix. and I have it written somewhere. Don't freak out. It's negative 3/5, 2, negative 11/5, and then 3/5, negative 1, 6/5, and then negative 2/5, 0, and 1/5. Okay? Now I want to do something here. I want to take this matrix and I want to multiply this by this little matrix without the x and y. Let's do that. Let's see if we can do this in our head. So I need to multiply this by that, right? So this will give me negative 3/5 times 1, right? Plus 2 times 3 plus negative 11/5 times 2. Is that right? Who's with me right now? I think only Louis and you guys. Are you with me? Okay. Scroll up. Stop taking notes. We're talking.
Yeah, no, I stopped taking notes so I could just listen.
Okay, good. So what is this number? Check this out. It's going to be nasty, but look, negative 3/5. I kind of know the answer, but 22/5, right? So what is that? What is the common denominator? 5, so that makes it negative 3 plus 30 minus 22, right? I turned 6 into, well, not 11. It's 5/5, right? Equals 1. So this first entry in this matrix is 1. Now let's do this again. First row times the second column. So that would be negative 3/5 times 2 plus 2 times 5 plus negative 11/5 times 4. Right? You with me? Okay. I'm going to be kind of erasing as I'm writing this stuff because it's too much. But this is negative 6/5 plus 10 minus 44/5, right? Well, actually, I don't have to do the whole common denominator. If I just add this two, so it's negative 6 minus 44 over 5, so that's negative 50 over 5, which is negative 10. And I still have a positive 10. 0. All right. Whoa. 0. Right? What would be awesome to happen in the third place? Another 0. And what would be really juicy to be here? 0. And then 1. And then 0. And then 1. So if I perform the computation, it's going to fall out like that. It will. I mean, let's just test one of the numbers. Let's test that one. How do we get that one? We have to multiply the second row by the last column, right? So if I do that, we get, so negative 3/5 minus 3 plus 18/5, right? Negative 3 plus 18 is 15/5 minus 3. 3 minus 3 equals 0, right? But the biggest thing here, remember when you said to solve the equation, you divide both sides by the constant? So if I multiplied the left-hand side of this equation by this ugly-looking matrix, I will have to multiply the right side of that equation by the ugly.
The bottom row. On the left,
Well, you'll do the same thing. You go this bottom row times the first, the second, and the third, and you'll get 0, 0, 1. Oh yeah, you have to do 9 computations like that. We'll discover that a little later. No, we don't know how to produce that. I just told you, let's say I know that. I'm just trying to inspire you feeling that, oh, I wish I knew how you come up with that. But the thing is, if I know beforehand that this is that special matrix, I don't need to do that computation. I know the answer is going to come out like that. All I need to really compute is the product of this fraction matrix with the right-hand side. And that product will be the solution to that system. So instead of doing that Gaussian elimination, I can perform this kind of a funky computation. Let's see if I can copy this matrix. And I'll copy this matrix. So I'm multiplying the same thing on the right. So whatever that is, only it's a product now. Yeah, so all I have to do it's going to be pretty fast, right? It's negative 3/5 times 2 plus 2 times 1 plus negative 11/5 times negative 1, right? And then I have to do this row by that column. So that's 3/5 times 2 plus negative 1 times 1 plus 6/5 times negative 1, whatever that is. And then I have to go this row times that column. So that's negative 2/5 times 2 plus, well, 0, and then plus 1/5 times negative 1. Whatever that is, that'll be my solution. Because I'll get my identity matrix on this end, and then something else on the other end. So I'm done. So whatever that is, it's negative 6/5, right? Negative 6/5 plus 2 plus 11/5. So it's nothing pretty. Actually, it is pretty. Ooh, it's pretty. Look at that. It's negative 6 plus 11, that's 5. 5 over 5. It's 1, so it's 1 plus 2, so that's 3. Ooh, 3. The other one is 6/5 minus 1 minus 6/5. Woo! Negative 1. I'm so excited. I didn't expect it to come out to be that pretty because I was making stuff up. And then negative 4/5 minus 1/5 is negative 5/5. It's another negative 1. That's the solution to that system. 3, negative 1, negative 1. Boom! Oh, I know. I wish. I should have done it with the mic. System. That would be the solution. Now, of course, that was just me being very lucky by knowing that matrix in advance. This is called the inverse matrix. Just like you have additive inverses, multiplicative inverses, this is the multiplicative inverses. So the idea is, if you have a system A times X equals B, then to solve the system, you just kind of multiply both sides by the inverse. This is inverse of A. Now the product of a matrix with its inverse is always going to be the identity matrix. And the identity matrix times any matrix is that any matrix. So really, it is just X equals inverse times B. So that's how you solve equations, systems of equations, mimicking the linear approach. Because when you said divide both sides by a number, you're multiplying by the inverse of that number. Same thing here. So we're going to So I just covered sections 9.3 and 9.4. 9.3 was all the Gaussian stuff. 9.4 taught you how to multiply and add matrices. This is 9.5. 9.5 starts with matrix inverses. So I'm not going to teach you how to find the inverses, because finding the inverse is another pain in the ass process. It's not trivial. Yeah, if you know in advance that's the inverse. There are shortcuts. Yeah, so that's the inverse matrix. Now, how to find it, that's a different story. But anyways, you're ready to do quizzes 10 and 11. Quiz 11 is not due till December, but do it early because you're going to have 2 quizzes back to back. But this is kind of, I like that. This is